Okay, so this is electrochemistry, which is the last part of module 14, and this deals a lot with kind of just the reduction potentials and so forth of a cell, like how many volts it needs for it to actually happen, for it to reduce, and so forth. So the first thing that we're going to deal with when it comes to electrochemistry is the galvanic cell, which is essentially just kind of a diagram of showing you how things are reduced and oxidized. Like it's just a real world example of it. And with a galvanic cell, you have components to it known as the cathode, the anode, and the salt bridge, which the salt bridge is just really what connects the cathode and the anode. Like it's just what allows the transfer to happen because it's a salt with both common ions of whatever you're doing. Right. So then your cathode is going to be where the reduction occurs. So cathode is reduction and anode is oxidation. So there's another mnemonic because this module is kind of full with them of how you can remember a cathode versus anode, which is red cat and ox, which is just red is the reduction, cat is the cathode, an is the anode, and ox is the oxidation. So red cat and ox. Yeah, I know, it's kind of silly, but it'll help you remember because it kind of goes with the equations that we have to do with galvanic cells and reduction potentials. So then something else that you might encounter with galvanic cells is something known as the cell diagram, which isn't really so much a diagram as it is just a special way of writing an equation. So if we take, for example, the equation zinc solid plus copper ion, and this is aqueous, yields zinc ion, also aqueous, plus copper solid. So then, again, if we were to figure out what's being reduced and what's being oxidized, we just look at our oxidation numbers. So 0 for our elemental states / stable states, which is solid, liquid, and gas. And then, not gas, solid and liquid. Not gas, my bad. So then this is going to be +2, and this is +2. So then zinc is going from a 0 to +2, which means that it's losing electrons because it's becoming more positive. So this is our oxidation. And then copper is going from 2+ to 0, which means it's gaining electrons because it's being less positive. So then this right here is our reduction. And I'm saying that because when you're writing the cell diagram, you essentially go zinc solid, and then there's a solid line which stands for oxidizes to zinc 2+ aqueous, and then this double line, which is the salt bridge that I said just has ions that allows this to flow. Okay, yeah. So it's zinc oxidizes to zinc ion, salt bridge, copper ion, aqueous, reduces, which is a solid line, to copper solid. And that's your cell diagram. It's essentially just a condensed state of, well, a condensed version of this whole equation right here. And I'm telling you what's happening in it. Like the zinc is being oxidized to zinc 2+, then there's a salt bridge, and the copper ion is being reduced to copper solid. And that's just a summary essentially of what's happening in your galvanic cell and in your reaction. So yeah, that's kind of the conceptual or just kind of the practical form of like a galvanic cell and the way that you're going to see it written down. So then we're going to move on to the next thing, which is the standard reduction potentials, which is the standard EMF of a cell. Standard reduction potentials, and standard EMF of cell, which, oh my god, cell has two L's. What am I doing? There we go. Which I know it seems like a lot, but they go with each other. So essentially ow, I just hit myself. Sorry. So essentially what a standard reduction potential is, it's just that in principle every element can be reduced, but some elements require different conditions for it to happen. So then the standard reduction potentials are the numerical quantity of just how many volts I need to reduce like a compound or an element, right? So then the standard reduction potentials have a 0 point, like where they're based off of, and that comes from hydrogen. And then from the base of hydrogen being reduced, they figure out how positive or how negative the voltage needs to be for a different element to be reduced, which I know is kind of funky, but it's just kind of think of hydrogen as your base, and the reduction potentials are just how different they are from hydrogen reducing. So then essentially, let me go into black. The more positive a reduction potential is, the better it is at reducing. So it's easier to reduce the species if it's more positive. And then, so the opposite is also true, where the more negative a reduction potential is, the easier it is to oxidize. So yeah, if you ever have a question where it's like, which one of these is the reduction / cathode, or which one of these is the anode / oxidation, just remember the more positive one is your reduction and the more negative one is your oxidation. So yeah. So then now moving on to the standard EMF of a cell, just because like I keep telling you, they kind of go together, is that you're going to have the formula where E naught cell is equal, or like E overall, E total, it's just the E of the cell, the EMF, is equal to the E standard of your cathode minus the E standard of the anode. And then, okay, so usually the tables that you're given for these problems, because you are given a table, you're not expected to know the E cell or the reduction potential of anything, because it's a lot to memorize, because there's a lot of elements. They each have a reduction potential. So if you need it, they'll give it to you in the problem. But since they're reduction potentials, if it's the anode, that's where your oxidation is happening, so the sign needs to flip. But while using this formula, the negative sign already flips it for you, so you don't have to change it at all. And I'm just going to say that because I know that there's another formula where it's like E of reduction plus E of oxidation equals E cell. Just forget that that formula exists. Just use the minus one because it does the flipping of the sign for you. And like you don't have to change anything on the table. You just get your math done and over with. So then rules for the E cell is that if the E cell is positive, And then your reaction is spontaneous in the forward direction. So then, if that's for the positive, if your E cell is negative, then the reaction is non-spontaneous in forward direction. So then let's do an example calculating the voltage of a galvanic cell, which is just using this formula because your E naughts are always in volts, which I didn't write down, but just know that your E naughts are always in volts. So then, example, we have the cell diagram that calcium solid oxidizes to calcium ion, salt bridge, aluminum ion, aqueous, reduces to aluminum solid. And then it gives us that for aluminum 3+ to aluminum solid, your E naught is equal to negative 1.66 volts. And then for calcium, I forgot the L in aluminum, your E naught is equal to, oh my god, is equal to negative 2.76 volts. So then just using this formula to find our E naught overall, or E cell, they're the same thing. We do our cathode minus anode. So if you guys remember what I said, the red cat and ox, your cathode is your reduction, which is the aluminum. So we would have negative 1.66 volts minus the anode, which is our oxidation. Then we would do negative 2.76 volts, and we just subtract, and we should end up with 1.1 volts as the overall E naught of the cell. So yeah, these aren't too hard to figure out. You just have to know what your reduction is, well, what your cathode and what your anode would be. And usually, like I said, it's in the formula. So if they had given you the equation, you would have to figure out what your reduction is and what your oxidation is with oxidation numbers. But like I said before, they give you the voltage. Or they give you at least one and the overall, and you have to figure out the other one, but like, that's neither here nor there. That's just algebra. But yeah. So that's what it is for the E overall, essentially. And you guys know I say this every time, but everything's related in chemistry. So you have spontaneity, free energy change, my bad, and cell EMF, which is the E naught, just in case I didn't say that. But yeah, so everything's related. So the way that you would calculate them is essentially that your delta G is equal to negative NF E cell, or if it's in standard state, it's your delta G naught is equal to negative N of your F E naught cell. And then your delta G is your Gibbs free energy. So free energy. N is your moles of electron. So not to get confused with moles of something else, like moles of a different ion. The moles of electron just means how many electrons are moving in the thing overall. And then F is, oh my god, Faraday's constant, which is 9.647 times 10 to the fourth coulombs per moles of electron. And then E cell is the cell EMF. So yeah, this is really, you just plug everything into the equation. Like, you're good. So then you have, like I said, everything's related. So you have standard EMF, and equilibrium. Yeah, I know, these things don't ever leave you guys. So the equations that we use for standard EMF is the E naught cell is equal to 0.0275 volts divided by moles, divided by moles times ln of K. And there's another version with the logarithmic. Instead of ln, it's the actual log base 10. And the only difference is the log base 10 in this number. But to just not confuse you guys, we're just going to use this one equation because it's the one that we use the same. And then, like I said before, E is your cell EMF, N is your moles of electron, and then K is your equilibrium constant. And then the V is just voltage. It's not another exponent that you're solving for. So let's do a practice problem with just solving for K, essentially. So we have the formula. Let me give myself more room before I mess myself up. That should say example for EX. So we have zinc plus copper 2 plus yields to zinc 2 plus copper. So then the problem, it would tell me that the E naught cell overall is equal to 1.101 volts. And if it didn't give me that in the problem, then we would solve for it just using the table or the values that they give us. And then our N is equal to 2, just because we can see here that we just have a 2 plus and a 2 plus, right? Like there's 2 electrons moving around in the whole equation. So N is equal to 2. And that's all we need to plug into this equation. Oh, I don't know what happened to my voice there. So then we just plug in. So we have 1.101 volts is equal to 0.275 volts divided by 2, ln of K. So then we end up with ln of K is equal to 85.6 or something around those lines. And then the volts are gone because we all know that K is unitless, and either way we're dividing by volts. So then we raise it to the E, or E raised to 85.6, and then that cancels out, so you're left with K is equal to E to the 85.6. So that K should be around 1.62 times 10 to the 37. Which, yeah, that's a big number. But, yeah, that's essentially how you use, oh my god, I'm so sorry. That's essentially how you use this equation to just either solve for K, or if it gives you other things, just to solve for whatever component is missing, you know? So then there's a relationship between our EMF and our equilibrium, obviously, because, like, they have to be if we have a formula for them. So if we have K is greater than 1, which is product favored, then our E cell is positive, and our delta G naught is negative. Therefore, our reaction is spontaneous. And then if K is less than 1, which is reactant favored, our E cell, or our E naught cell, is negative, delta G is positive, therefore our reaction is non-spontaneous. Yeah. And then finally, if K is equal to 1, product equally favored to reactant. Our E cell is 0 and our delta G naught is 0. Therefore, there's no reaction. No, let me write that down better because that looks kind of bad. So then our delta G naught is 0, and therefore there's no reaction happening. And yeah, those are our relationship standards between K, G naught, and E naught. So yeah. And then finally, we're going to move on to the very last part of our thing. Let me slide this back to over here. So the very last part of electrochemistry, which is the Nernst equation. I don't know if I'm pronouncing that right, but it's spelled like that. So then this is going to be a lot of kind of just what it is. It's essentially like the other equation that we had, except that now instead of at K, it's at Q. So we have E naught, no, not E naught, just E, because we're not dealing with actual, because we're dealing with something actual, not the standard state. So we have E is equal to E naught minus the whole equation that we did right now, which is 0.0275 volts divided by N times the ln of Q. So E is the actual reduction potential of the cell, like not the reduction potential, the actual cell EMF, and then E naught is the standard cell EMF, which is what they usually give you in the tables and values. And then, like I said, N is your moles of electron, and then Q is just your reaction quotient. So this just means that your reaction isn't at equilibrium, which means that it's not in its ideal standard state. Since it's not at equilibrium, it's at something else, which is why we have this E without the E naught, because we're not at an ideal standard state. We're in real life in this moment. So then, yeah, it's just kind of you plug things into it. So we can do an example where it's essentially we have tin 2 plus aqueous plus bromine liquid yields tin 4 plus aqueous plus 2 Br minus aqueous. And then it tells me that the initial concentration, well, not initial concentrations, but just concentrations of these things are 0.05 molar, 0.05 molar, 0.00, okay, it's another 0, 1 molar, and 0.0001 molar. So if we're going to write our Q expression, because I just want to solve for that first before we do anything else. So Q is equal to our concentration of products over our concentration of reactants. And that's going to be our concentration of SN 4 plus times Br minus squared all over just SN 2 plus, because bromine is a liquid and we don't deal with condensed states when we're doing our reaction quotient. So then we just plug into it so that we have 0.0001 times 0.001 squared all over 0.05, so that our Q should be 2 times 10 to the negative 11, or along those lines. That looks like a 14. Let me write this down prettier. 2 times 10 to the negative 11. All right, cool. And then the problem does give you the E naught cell, it being 0.93 volts, which is a nice problem because some problems won't give it to you. And like I said, we'll have to use the values that it gives you. So then we just plug this all into the equation so that we have our E is equal to 0.93 volts minus 0.0275 volts divided by N, which is going to be 2 electrons, just because there is only 2 electrons moving. Like, you get the 2 pluses are initial, and then this one loses 2 electrons, this one gains the 2 electrons, so 2 electrons. Time divided by 2, ln of 2 times 10 to the negative 11. So then we do all this math, which should give us 0.93 volts minus a negative 0.391 volts, so that our E is equal to 1.24 volts. And that's the actual cell EMF of our reaction in this case. So yeah, this is it for electrochemistry and module 14.